So we're getting to the end of chapter 1, equations and inequalities, and now we're going to have some word problems. Section 1.7 is problems involving interest, mixtures, uniform motion, and constant rate job applications. So the first thing that we're going to do is translate verbal descriptions into mathematical expressions. So this is just practicing turning the words of the word problem into the mathematical language that we need to be able to solve the problems. Then we're going to solve interest problems. And solve mixture problems. Solve uniform motion problems. And solve constant rate job problems. Okay, so the first objective is going to be to translate verbal descriptions into mathematical expressions. And an equation that describes the relationship between variables is called a mathematical model. And if you think back to that first week, we talked some about what is a mathematical model. One really popular one you see in chemistry is called the ideal gas law. It says the pressure times the volume equals N, the number of moles, times R, the ideal gas constant, times T, the temperature. So this is a model that says if you know 4 of the things, you can figure out what the 5th one has to be. And it seems to very closely model what we see in actual fact if we do experiments with gas and changing the pressure and the volume and the temperature. So what are the steps in solving applied problems? Read the problem carefully, and you may need to read it 2 or 3 times, sometimes even more than that. And maybe underline important words, and especially look for numbers. And then also be sure to look for the question word in a problem to figure out what should the variable stand for. So you need to assign a letter to represent what you're looking for. And I want very detailed description like X equals pounds of African coffee. So I don't want to see X equals pounds. And I don't want to see X equals eggs. So it needs to be very specific. And then change the words that you're finding in the problem into mathematical symbols. So it takes a lot of practice, but I promise the more you do it, the better you will get at it. And some of it needs to be from practicing and seeing patterns, because there's a lot of patterns in these problems. So word problems usually have units associated with the answer to the problem. For instance, hours or miles per hour or some kind of way of measuring. So your answer needs to have units on it. And your answer must be in a complete sentence that begins with a capital letter. So the second objective is going to be to solve interest problems. And interest can either work for you when you're investing or lending money, or against you when you're borrowing money, which is what you're doing when you use a charge card if you don't pay it off completely. So interest is the cost of using money. And I haven't charged my kids interest. If they needed to borrow $50 to buy a corsage for a prom, we'd say, okay, fine, but I need you to pay me back $55, and that's for the privilege of using my money instead of your money. So that's what interest is. The original starting amount of money is called the principal. So capital P gets used most often for that. You can also think of it as the present value. And you'll hear that a lot in business applications, and in engineering we would talk about it also, of if you have a future expense, how much money do you need to save now to have enough for the future expense? So that's the present value. And the variable we use is this capital P. The rate of interest is usually quoted as a percent, but it has to be converted to a decimal to use it in interest calculations. And we use the lowercase letter r for this quantity. So remember, 10% equals 0.10 as a decimal. 25% equals 0.25 as a decimal. And 1% equals 0.01. And usually the amount of time is in years, but occasionally it will be in different units. It has to match the time period for the interest rate. And we use the variable lowercase t for time. So the simple interest formula says if you put P dollars in an account or borrow P dollars for a period of T years at a per annum, so that's an annual interest rate R expressed as a decimal, then the interest rate I charged formula looks like I equals PRT. So it's the amount you started with times the interest rate times the amount of time, and that's the interest charged. Or if you're investing, it's the interest earned. So the formula I told you about was a simple interest formula of I would charge my kids some percent of what they borrowed. So that's called simple interest. And when this formula is used for computing interest, then that's what we define as simple interest. And that's as compared to compound interest, which we'll look at later when we talk about exponential functions. So we're going to do this problem in class together so that we can work it out. And I just wanted you to have all the basics before we started. So we'll do that one in class. So objective 3 is mixture problems. And any problem where you're combining two or more types of things to make a mixture are called mixture problems. So it could be two different kinds of candy, two different kinds of coffee, different kinds of nuts. The helpful thing will be if you realize that they're actually all the same problem. So it could be pounds of African coffee mixed with pounds of South American coffee. You can tell I'm not a coffee drinker. And that's going to be a mixture problem. It could even be 10% fat chocolate with 15% fat chocolate. So anything where you're mixing things together. So again, we'll look at this problem together so that we can work on all the steps of solving a word problem. And I would practice these, because I don't pull rabbits out of my hat and give you strange problems. I give you problems like ones you've seen before. Okay, so the next objective is to solve uniform motion problems. And the word uniform is used here to mean unchanging. So it's whatever speed is happening doesn't change. So if you're going 5 miles an hour in the problem, you keep going 5 miles an hour. If you're going to allow the speed to change, that's when we need calculus. So we're going to stick with uniform motion. And if objects travel at a constant speed, they're said to be in uniform motion. And another way of saying this is that there's no acceleration, because acceleration changes your speed. So if an object moves at an average speed rate r, the distance d covered in that time is d equals rt. So I remember this formula as distance is rate times time, or the DIRT formula. Okay, so then we're going to do number 28 together in class. And just so you're already thinking about it though, if I have a river and I'm traveling in the river and the current is pushing this way, when my boat is going this way, the current is helping me and its speed is adding to my boat's speed. But when I'm going the other way and the current is pushing at me and my boat's going this way, the current is subtracting from my boat's speed and slowing me down and making it take longer, right? Okay, and then the last type are going to be the constant rate job problems. And the key to solving these is to realize there's lots of similar problems when people, machines, water pipes, printers, copiers, anything like that are working together. The thing that combines is their rates. So their rates are what add together. So really, these are the same kind of problems as the last one. If you think of the rate that you're working at as the r from the distance is rate times time, and you just think of distance as what you accomplished. So in a distance rate time problem, it's how far you traveled. But in a problem like this where you're printing things, it's how many did you print? But really, they're very similar in nature. So we'll do this one together again in class. And that's it for section 1.7.